Good afternoon. I hope you all can hear me. Hope to get started here in just a moment or two. We'll let a few more stragglers trickle in. All right, then we'll look to get this started, I guess, right now. Thank you all for attending. This is the latest in the Post-Global Resistors webinar series. We started it last year. We're continuing it through this year. Today, we will be looking at variable frequency drive braking or overhauling applications, regen or resistor. We'll try and look at some different cases where it would be required, some solutions on what to do with this now potentially excess energy, and what the cost ramifications are of choosing one over the other. I'm going to issue the caveat now. Obviously, we're a resistor manufacturer. We're slanted maybe one way better than others, but we're going to do our best to present this objectively and give you some things to think about, some takeaways, and some things you can consider for your next drive application and whether or not one method might be better than another. By means of introduction, my name is Stu Gibbon. I've been with Post-Global now for just over 20 years. I have an engineering degree, but thankfully working for a resistor company, I only had to remember V equals IR, which made my life a whole lot easier. As a way of hopefully taking care of some of the questions that will come in during the course of this based on history of these presentations. If you registered for the presentation, you will receive an email with a link to the video, so you can download, watch it later, share it with your friends, and a certificate of participation that you can use for your continuing education credits. If you'd like a PDF copy of the presentation, please either email me, stugibbon@postglover.com. You can also reach out to your local manufacturer's rep of ours, or reach out to the outside salesperson who calls on you, and they can steer you in the right direction and get that into your hands. As we're going along, because I can't actually see or hear anybody, please feel free to ask questions using the questions tab on the right-hand side. I am running this without assistance today, but at the end of this, I'll click through that section, select some of the questions, and answer them in this forum. The rest of them, rest assured, we will get back to you personally and answer your questions. So if there's anything you'd like to know, if there's anything you would like us to follow up with you on, feel free to make a note of it there in that question section, and we'll get back to you. So what are we hoping you can leave here in 45 minutes to an hour and say, here's what I got out of this? We're hoping to explain, what happens when a variable frequency drive either needs to stop or needs to slow down or maintain a speed. There are many load conditions that present unique challenges in terms of energy created that needs to be dissipated or otherwise reused, and that's what we're going to be addressing. We're going to look cost-wise at two main types of energy remediation, but also discuss several other options that may be available to you depending on your particular situation or criteria and the money or the budget that you have set aside for this particular job. We'll also, at the end of it, like I said, go through the questions as best we can. We'll pick some out. I realize everyone has allotted a certain amount of time for this presentation. We're going to do our best to keep it within that time frame, but still manage to hit some of the highlight questions and get you some answers on those. So variable frequency drive basics. I'm going to go through a little bit here. Postclover has done over the last, I'll say 12 months, 2 other presentations on variable frequency drives and dynamic braking resistors. They are currently on our YouTube channel. I'll put a link up at the end. So if you'd like to go back, review those, or if you'd like a link to be able to download those, please let us know. We'll be happy to get them to you. Variable frequency drive, on the very basic side of it, the drive is connected to an AC bus. That AC power comes in, is rectified, and we get a main DC bus in the drive. That DC bus now can be chopped into a new waveform of varying frequency, which can allow us to control the speed of the motor. Can lift a load, can move a conveyor belt, can operate a fan. The output of those IGBTs allows us to create a different frequency waveform and adjust the speed of the motor appropriately. When we're talking about motors and we're driving a load, that's what they call motoring. So when we're in motoring situation, there's no excess energy that needs to be taken care of, and everything's fine. The problem comes in when we end up in a situation where all of a sudden that motor isn't pushing the load is theoretically pushing the motor. So now that motor stops acting like a motor, starts acting like a generator. And we start forcing energy from the load. The kinetic energy becomes electrical energy, and now we're trying to force that back toward that AC bus. In some instances, very low energy, this can be handled. In most instances, there has to be a solution for how to deal with that so the drive itself doesn't get damaged. We've seen various mishaps where a drive basically acts like a fuse. If you sell drives, that's a great idea. You get to sell another one. If you don't, this is a bad idea. Your production is now shut down. You've got to replace it. You've probably got to replace other components. So during the braking phase, there has to be a way of dealing with that extra energy. So when I say braking, there's actually 2 separate forms of that motor forcing energy back into the drive. So the first one is literally braking. So for some reason it's a process where the motor has to come to a stop, or potentially an e-stop type, or we need to decelerate in a uniform manner. So the energy that's in that motor has to be bled off. The field has to be drained so the motor can stop. Otherwise, it will go until it dissipates what's in it. Couple of ways of doing that would be, dynamic braking resistors. You could use a mechanical brake. You could also use some type of regen. But braking is typically a one-time stop, and the energy and the speed go to 0. The other phenomenon where we're going to have energy coming back into the drive is what's called an overhauling load. So this may be a conveyor belt at Amazon that's actually on a downhill slope. So the weight of the packages is trying to accelerate that conveyor belt, and what we're trying to do is maintain the speed. So there may be some excess energy from those motors that we need to dissipate. Another example would be an elevator going down or a crane lowering a heavy weight. That motor is now trying to create something, or trying to find something to do with the energy that's being forced back into it. Some of the mechanical brake typically wouldn't work in these situations. So you're looking at either dynamic braking or some type of regen to take care of that energy. So the question now, and what we hope to address in this presentation, is what is your best solution, resistor or regen? So I'm sure everyone's got some ideas or has some prior experience on this application. Here's what I did, or with this customer or this project, here was our better idea. The two ways basically come down to, if you're looking to choose a braking resistor, you're looking to take the excess energy, shunt it out of the drive, and dissipate it as heat. You basically connect a big industrial toaster to the drive, and when that DC bus in the middle of the drive that we showed, when the voltage on that gets too high, we flip a switch and we send the excess energy into the brake resistor and we dissipate it that way. The other option would be, can we make use of that energy somehow? So my drive, or the motor that I have, is now trying to force energy back into the drive. Instead of dissipating it, can I somehow get it back onto my AC grid within my industrial facility and use it elsewhere? Important to note that we're looking to, in regen situations, get that energy back onto the internal to the plant AC bus. We're not looking to then send it back out to a utility transformer, send it back onto the grid and get some kind of credit from the utility for it. This is power that we're now trying to put back and use internally in our facility. So the first one that we'll take a look at is the dynamic braking resistor. As I mentioned, you've got a sensor on the DC bus with basically a switch on it. When that DC bus voltage gets above a turn on voltage, that switch closes, and now all of a sudden the braking resistor is getting the excess energy. So in an e-stop type application, or we need to stop something in a controlled fashion, that may close for 1, 2, 3, 10 seconds. We bring everything to a stop and then it comes off. In the instance of an overhauling load, for example, we have a port crane lowering something several hundred feet, that motor will now be seeing a regenerated power, will now be trying to force power back into the drive 10, 15, 20, who knows, maybe a minute if it's some type of long mine conveyor belt. So the resistors have to be rated accordingly, and the amount of energy that is now being forced back through and dissipated through the resistor can vary greatly. Those numbers that vary, the amount of energy, how long, that sort of thing, will go a long way later to deciding which way do I want to go between using a resistor or finding a way to make use of that power some other way. So as I explained, dynamic braking resistors, they're fairly straightforward, and I think most people, it's the solution most people are familiar with. So when my motor tries to force back through the inverter to the DC bus, if that DC bus voltage gets too high, the chopper, which is built into most drives now, if you go back 20 years ago and look, the chopper module was probably an external box that had to be connected. Now it's pretty much built into all of them. That chopper will now redirect the power to the resistor. The resistor burns it off. The drive doesn't see an overvoltage. There's no damage. There's no reason to trip, and away we go. There are some considerations around that. The resistors have to be sized for the chopper circuitry and the inverters in your particular drive. Now, in most cases, for most major drive manufacturers, these resistors are already pre-designed. There's part numbers available. There's lots of catalogs. And depending on your voltage, depending on your drive size horsepower, depending on whether it's regular duty or heavy duty or other particular applications, you've got a resistor pre-designed that you can pick out, get a price on, and slap in to complete your project. So when we're looking at dynamic braking resistors, and admittedly, I'm probably jaded, I think they're wonderful devices. The advantages of a dynamic braking resistor, when we look at it as a solution for this issue, is they're relatively simple. There's 2 terminals you plug in. Relatively low cost. You're buying a heavily engineered piece of metal. So there's no extra electronics, there's no detection circuitry, that's already built into the drive. That's already accounted for whether you're using the resistor or not. Um, there are packages that are available for various duty cycles, packages that are available for various types, whether it's a decelerating, a stopping, or an overhauling load situation. Some of the disadvantages potentially for braking resistors, this energy that we had, this excess energy that we had, is now being lost as heat. So it's not being reused. We paid for it and we're just burning it off. The heat generated from these resistors can be a concern. Now, if it's a small one like the one shown in the backdrop here, it's probably not a big deal. You're not doing a lot of calculations or considerations about where to place them or what to do with them. But as they get larger, 50, 100 horsepower drives, the amount of heat they can generate, in particularly an overhauling situation, is something that just has to be considered in terms of how much real estate do I need, not just to mount this box, but around it for airflow and so that I don't melt something or burn something around it. You know, cable tray can't run 6 inches above a large resistor. You're gonna have to have a couple of feet there to make sure everything is safe. So one of the other ones, in addition to location, is what's the environment you're in? You know, if you're in a newsprint producing facility and there's shards of paper in the air all the time, it's quite the flammable environment. You probably have to figure out where to put your brake resistors to protect yourself against some type of issue. So that's our sort of pseudo review of dynamic braking resistors. We'll take a moment, we'll drop into our first poll question. I know what most of you are thinking of poll questions, but here, let's get this one launched. And I'm going to be honest, based on what I'm seeing from the poll results so far, apparently none of my coworkers here at Post Glove are paying attention to this presentation right now. I appreciate you doing that. Apparently 80% of you are actually paying attention to me today. Again, many, many more than my actual coworkers do. So now that we've taken a look at dynamic braking resistors, the other option we discussed at the jump was, can I do something with that energy to make use of it? Is there something I can do? Is there some other method? So there's a couple of different ways. You know, ideally, the simplest way is we'll just run this back up, we'll put it on the AC bus, and I'll use it somewhere else in my facility. How do I do that? We'll take a look at a couple of different ways. I'm not saying these are the only ways. Some of these are a little simpler, some are a little more complicated. But we'll take a look at some different options and see what might be better or applicable for certain applications better than others. So perhaps one of the easiest ways to do it is we combine the DC buses and the drives to form one common DC bus. And this is an example where there's two drives, so obviously a larger, higher horsepower one and a smaller one. We fuse the common bus connection between the two. So basically the second VFD derives its DC bus from the first. Ideally, one is braking when the other is motoring, and one is motoring when the other one's braking, such that any energy that is regened back onto that common DC bus can then be used by the other drive instead of you paying for more energy to drive. On the shared bus, you have an option there to kind of balance that load. So it's kind of a share the pain type situation. The issue with this being, depending on your application, if you run into a situation where both of those drives are in a situation where their motors are either overhauling or braking at the exact same time, there's nowhere to pick up the slack and use the excess energy, and you may still require either a braking resistor on that DC bus or some type of external regen unit to be able to take that up and make use of it without it becoming problematic and or damaging one or both of the drives. Another option, again, building on that common DC bus option, is, like I mentioned, you use a regen module or a line regen module. So in this case, that line regen module is going to be connected in parallel with that DC bus. So it's just another device on the bus. The difference being, in this case, if for some reason, in this case, we see main drive, back drive motors. If the motor on the back drive is regenning and that main drive motor isn't doing anything at the moment, or the main drive motor is regenning and the back drive can't take all that power, we now have an option for it to also be seen by the line regen module, here listed as the regenerative converter. It sees the DC bus voltage go too high, and what it does now is converts that back into AC and feeds it back onto the AC bus typically through current suppression reactors. It's a fused connection, gets it back on the AC bus and can be used by the rest of the plant. The trick with doing line regen or regen is that power has to go back in basically in phase with what's already on the AC bus. So it has to be able to rejoin that bus perfectly in phase overlap so that I don't have any issues there. So this line regen module can take the excess power and put it on. The advantage of the line regen module is I can keep using the same drives that I've always used. So I like working with these guys. I've got those. I can get a line regen module either through that drive manufacturer or distributor or through a third party who just does line regen modules, hook it up, and I'm good to go. The line regen module obviously has to be sized for the drives that it's going to be connected to, which means long-term you have to kind of know, do I need to upsize it in the beginning to be able to handle any possible expansion down the line? And that's something that, based on your individual projects, you'll have to make that decision. Now, the advantage we get here, obviously, is, yes, I've probably spent more on a line regen module than I have on a braking resistor, but I'm able to put some of that power back into the AC bus, use it somewhere else, and potentially lower my utility charges. So in this, I'm basically talking more about actual costs than, say, the cost on my conscience for reusing AC power or reusing power in a method that allows me to cut down on my consumption. So another option for multiple drives is what's called an active front end. So when we looked at that line regen module, it was connected in parallel on that DC bus. When you go to what's called an active front end, it is now in series and is basically providing the DC bus to any drives it's connected to. Some of the advantages of an active front end are you've usually got your harmonic filters built into that. So any issues with the rectifiers that IGBTs and harmonics created will be taken care of there. It has the line regen module basically built into that active front end. So common DC bus, 1, 2, all 3 drives are breaking at the same time. That bus voltage goes up. Your active front end sees it. Great. Let's shunt this back through input reactors through another harmonic network, and we get it back onto the AC bus where we can make use of it somewhere. Sizing the active front end, again, similar to the line regen module. In theory, it's summing up the drives that are going to be connected to it. you have to keep an eye out for, hey, what are my potential future expansion plans? Because obviously in this situation, if I size that active front end for those 3 drives and I need to expand later or I need to add a function, that active front end may already be maxed out and I've got to go add another one. So when you're looking at the cost of all that, you've got to take into mind, okay, what's my plan in the future? What do I think I'm going to be doing? Because I don't want to make a decision now that's going to cost me more money down the line to add to it. I did want to take a moment, kind of step out for a second. I know for a lot of people, and I'm going to say for my kids particularly, when they think of regen, they think of automobile applications. So they're thinking Prius or they're thinking Tesla. Obviously, the electric motors drive the wheels to go forward. When you try and brake, so a decelerating, a braking mode, those motors now act as generators. They send energy back. It's stored in the batteries. Now, if you ask my kids, they think this started with Toyota and Tesla. They have no clue. One of the things that, in taking a look at this technology has been around forever. Here's a picture of an electric car from 1906 that already had regenerative braking capabilities. The real reason I bring this up, and it's not just to pick on my children because they can't even hear me at the moment, Europe is already slightly ahead of North America when it comes to electric vehicles, be it trains, buses, electrified transport trucks. One of the regulations that they have in effect over there is for larger vehicles, especially for buses or large passenger vehicles, that you can use regen to repower the batteries. That's fine. But there must also be a secondary brake on it. Typically, this is going to be a resistor. This brake can be air or liquid cooled. And the reason I bring it up is, for all you guys, all you people in the drives industry, we're starting to see some of this European technology move stateside, both in vehicle applications and other applications where you've got, such as in a bus, potentially large amounts of energy that need to be taken care of in either a regen or a brake resistor type mode. One of the things they have been doing in Europe is creating a closed system with water-cooled resistors. What this allows them to do is, this is the secondary brake that the law requires. They've got a compact, self-contained system that they can therefore shunt excess energy to. It's taken care of, it's cooled. You don't have to worry about, you've designed heat shields and methods of dissipating that energy or the heat within the closed system, such that you don't end up with, superheated bus roofs or bus floors. So the comfort on the bus isn't affected. Just something to keep in mind if you run into vehicle applications. A water-cooled resistor may be something people are looking for certain closed-loop applications like that. We'll take a moment now and run through poll question number 2, just to make sure everyone who claimed they were paying attention the first time is still paying attention. And this is sort of a method. This question, admittedly, is a little selfish. We want to know, not only was this webinar a good idea and will it be well received, and is this information something people are looking for, but also what do we need to be looking at as a company in the next 5-10 years? So the basic the basic that we got, 30% feel that in the next 5 years, so that includes the 1 year and the 5 years, they'll be likely looking at this type of solution. 70% are probably still looking for bigger savings on and more, I'd say, bigger savings and a larger installed base to get a better comfort level with the regen situation. So the final solution that I'm going to be looking at is would be a Regen Drive. You know, a couple of years ago, 8, 10 years ago, everyone talked about, you know, 4 quadrant drives. And basically this would be a drive that has the line regen module built into it. So it's bidirectional IGBTs on the output side. If that motor starts getting into an overhauling or braking situation, energy comes back in, it's converted, you know, it goes AC, DC, AC back onto the grid and can be used in the facility. There are going to be, obviously, and we'll see in a little bit, applications that are better suited for this than others. Facilities that are better suited for this than others. Newer buildings, newer installations, you probably have a much better opportunity to install something like this and make good use of it than an older facility where you may have things to work around that this could cause issues with. We are starting to see more and more regen drives available in the market. You're probably, you know, for those of you who are end users, you're probably seeing more promotional brochures, literature, videos on how you could implement these in your facility. And I'm sure if there's any distributors or manufacturer listening, this is something that you're also looking at to bring to your customers now, because it's starting to get more into the ballpark of, hey, this is something you could do. When I take a look, and again, doing the cost comparison on these to me is proof that the applications work, but you need to make sure you pick the proper application to apply these. As a braking resistor person, I could tell you that, hey, braking resistors always work, they're always great, they're always wonderful. But there are going to be applications where you can see in a relatively short period of time, and that's totally dependent on every user what that relatively short period of time is. You may want to look at a regen drive situation because this might work out for you. So we kind of focused in on, you know, roughly 480 volts, 460, and we looked at a range of drive prices or drive sizes from 10 through 500 horsepower. So at the lower end of things, if we just look at the drive prices, you know, at 10 horsepower, the regen drive's 3 times the price. As we start to move up into, you know, 100, 125, it's maybe twice the price. And when you get up into, you know, 500 horsepower, it's only and I use that, you know, loosely, it's only 50% more to go to, you know, a regen drive. Now, if we factor in the resistor that would be required to get the same performance out of a standard drive, so we're comparing more apples to apples. You'll see that even adding a 10 or as large as a 50% duty resistor, your upfront, you know, layout on an installation is going to be higher on the regen drive still than it is on the standard drive for that same size drive, based on your personal criteria. But again, we've left out probably the thing that we mentioned a few times here is, what are my energy savings? What are my, you know, can I make enough back? You know, the utilities around here, you know, we get free light bulbs all the time to get us to switch over to LED, saying that, hey, you're going to save money on your bill and this will be great. Well, what I've found typically in my house is the light bulb is probably the smallest load that I have, and it's not helping me a whole lot on that bill. But if we take a look at, you know, what is the energy saved using a full-on regen drive, and what is my payback period going to be? Does it make sense to do this? So we set up the table, and now we're looking at applications. It's 10 horsepower, 100 horsepower, and 500 horsepower. if we go through the equation, which is, your horsepower in watts. So it's the horsepower times 0.746 gives me my watt usage. How many hours a year is it used? So if you take a look, I've chosen a few different scenarios, and I'll explain why in a moment, why I picked them. But it's how many days times how many hours a day. What's the duty cycle? So what's the duty cycle on braking? So on all of these, I use the same 10% duty cycle, just so we could compare sort of within the comparison, apples to apples, without jumping around too much. And then the cost per kW. We took a national average, a recent number, so we can apply it. So these numbers are fairly realistic. So if you had a 10 horsepower drive with a 10% duty cycle on braking, and you ran it every day, all day, over the course of a year, you'd save $425. Now, I know all of you are probably sitting there trying to think back to the last slide and how much did it cost. We'll get to that. Don't worry about it. If you look at 100 horsepower, now in this scenario, what I did was okay, you work 5 days a week, 50 weeks a year, 10 hours a day, same thing, 10% duty cycle. I'm now saving, $1,400 a year on my energy savings. And when I bump up to a 500 horsepower drive, same thing. 5 days a week, 50 weeks a year, but I'm now running 2 shifts. So I'm running 16 hours a day. My energy savings are potentially $9,700 a year. I'm sure, as most of you thought, the larger your drive, the bigger the energy savings if you can use regen in some form or fashion to be able to make use of that. This has been borne out clearly. So what we've done now is, gone back, figured out the payback period. So on a 10 horsepower drive, if I take the cost of the regen drive, subtract the standard drive and the 10% duty resistor, divide that price difference by $425 annually, it'll take me 13 and a half years to save back the money and offset the higher price of that regen drive. At 100 horsepower, I'm looking at 4.5 years. So in both these scenarios, I'm looking at that line's got to be up, running a good amount, fairly consistently with no changes, for at least 5 years for me to get my money back on that regen drive. Admittedly, when I go to the 500 horsepower scenario, now I'm looking at 2.5 years to get payback on that regen drive. And I think if we had done the first poll question instead of me trying to ask if anyone's actually paying attention, if I'd said, where do you think this starts paying off? I'm willing to bet most people would have bet 500 horsepower. From our side, from the resistor manufacturer, we don't sell many resistors for 500 horsepower drives. So clearly people are doing something else at that level. This might be the option that they're looking at. Because obviously 2.5 years, that payback period may be enough to say, look, my production processes aren't going to change in the next 4 years. I can put in the more expensive drive and make the money back and come out ahead long term. So a quick recap on this. As I said, resistor brakes are cheap to buy. Cheap means they're less expensive. Comparing the price of standard drive versus regen drive, the resistor brakes are pre-designed, delivered quickly, fairly easy to install. So the overall price of them is fairly good. Resistor braking is wasteful. I picked this because it was more of an impactful statement than getting into environmental awareness and whatnot. It's, we have this excess energy. We have elected on a cost basis to dissipate it as heat as opposed to trying to find something else to do with it. If you're looking at using a regenerative braking solution, it's going to be more complicated and it's going to be more expensive. even using a Regen Drive, you're looking at more expensive. However, Regen could have some other advantages when I look at the size of the drive. Now, a Regen Drive is going to be larger than a standard drive due to the Regen function that's built into it. However, I don't need to place a resistor somewhere. I don't need airspace around the resistor to allow for cooling. And hopefully I'm getting enough energy savings on it to offset that higher cost. So again, it's a per case decision. Is this the way I should be going? So quick summary, obviously, when you're in a situation, VFD in a motor, you want to stop the motor. You want to slow the motor. That energy's got to go somewhere. You can use and I'll call it the time-honored tradition of using a resistor and the integrated chopper within the drive. Easily done. Everyone's familiar with it. Off it goes. There's 2 wires to connect that resistor. There's no polarity. You just wire them in. There's potentially 2 other wires if you're using a thermal switch in the resistor, such that if the resistor heats up too much, you can then, one of the things I will say is the thermal switch that's in the resistor is basically there to say, hey, this resistor is seeing more energy than it was designed to do. There might be something wrong in the drive. Let's shut the drive down to prevent further damage. Another quick aside, just throwing in. The last option is this energy that's created, during a braking or an overhauling situation can be converted back to AC using Regen, put back on the line and used somewhere else. It's a little more complicated and therefore costly, but the efficiency may be what you're looking for in your particular application and may be useful to you. So I will attempt now to jump into some of these questions and see what I can pull out. I think I may have gotten away with it. I think you guys were pretty nice on me and didn't ask a whole ton of questions. I will say, like I mentioned earlier, our other DB presentations, as well as others that we've done in this series, are available on our YouTube channel. Yes, that is a ridiculous URL, and none of you are going to remember it. However, if I can get 100 people to subscribe to the channel, I'll give it a much better name. It'll be much easier to remember, and you'll be able to get there much simpler. That is not a shameless plug to get followers, but heck, I'll give it a shot. So the question came in about, and thank you, Lorenzo, for asking the question. The question came in about what would be considered common practice, best practice for industrial elevators. My understanding, or what we have seen, is yes, a lot of elevator manufacturers are moving to a Regen Drive. However, there is often a secondary, similar to what we saw on the bus. There is a secondary sort of fail-safe option where if something is above ratings, they can dump to a resistor or dump to a secondary source in a hurry to avoid. I can take a look at some various sources we have here and get you some ideas or some papers that have been written on that. If anyone else is interested in elevator drives and how they're dealing with the Regen, feel free to let me know and I'll reach out as well. I got another question from Al. Do you feel the government might push you to replace resistors to regenerative means? I don't know if they will push. I do not feel they will push post-Glover. I believe if there was a move to go that way, it would be similar to the car industry. They'll look to either subsidize the technology or give you some kind of credit for doing that. As we are, we're like the brake pad supplier to the car companies. So they're not going to hit us up to say, hey, if you guys build a battery, it would be better. they're going to push the car manufacturers to make better choices. So they're going to go out to, the distributors and say, hey, we're looking to switch more users over to this. So, and somebody did ask, Bob just asked about, we said, DBR, regen, or both, when to use both. So one of the things we looked at was, for example, the DC common bus, where you're basically regenning from one drive to the other, but may still require a separate resistor for extreme conditions or conditions where you can't use up that energy. Or as we just mentioned in applications like elevators that are up and down all day long, regenning all day long, and they may incorporate a safety fallback position of a brake resistor, such that if something happens with the regen, they're not going offline with that particular elevator. They can make use of it, the braking resistor, and keep going. I personally want to thank you all for participating today, for listening. I appreciate you tuning in. If you've got any questions, again, my email address is up there. You can also feel free to reach out to your local post-Glover manufacturer's rep, or get in touch with one of our outside people, Chris Small, Joe Campa, Rob Gannemiller, or Steve Fisher. They'd be more than happy to help out, get you answers, and help you with any technical information you need, either on our product, or they can help you find what you're looking for on something related. Thank you very much for tuning in. The emails will go out shortly, and I appreciate you all coming along. Thanks. Have a great afternoon.